We're going to start by talking a little bit about the different types of transformations that can be done to a parent function. First, we have to understand what a parent function is. So a parent function is like the simplest form of an equation that generates a certain shape. So in this case, we're looking at a whole bunch of absolute value graphs. So the parent function is y equals the absolute value of x. So notice there is not a lot going on in this equation. We see an x and a y and absolutely no numbers. The only thing we see is the absolute value bars generating that V-shaped graph. Now, we've looked at this absolute value graph before. We know that we could make an XY table to describe what's going on here, but we also just basically know that that's what that looks like. So we want to start to get a sense of how could we graph without having to do so much plugging in of numbers. We want to start to recognize some of these transformations. You'll study this a lot more in Algebra 2. This year, this is sort of just an introduction. So the first thing we see is something called a vertical translation. Remember back in middle school, you learned that a translation is the fancy word for sliding something around. And notice, if you look at that absolute value graph, it looks like we just slid it up 2 spaces. It's this +2 outside the absolute value that accomplishes that. Adding 2 to the outputs moves each y value up 2 spaces. So notice, if I had the point 1, 1, that would have been right here. It moved up 2 spaces. Same with the vertex, 0, 0, it would have been right here. It moved up 2 spaces. And any point we pick on the original absolute value graph, we would see it was 2 spaces higher than it used to be. So that's what we call a vertical translation. Next, we're taking a look at a horizontal translation. So still the word translation, so it's still a slide, but this time it's a slide to the left and the right. Here's the confusing thing. When we saw +2, it went up, and that made sense because y is up in the positive direction. But notice, this is +2 again, and it's a horizontal translation. It kind of feels like it should go to the right, but notice it doesn't. It goes to the left. This is a little bit connected to the point slope form that we've been studying in this unit. If you imagine this as y equals the absolute value of x minus a -2. Notice the minus is actually going to be part of the formula. The way the minus is part of the formula in y minus y1 equals m times x minus x1. That shows us the -2, which is where the vertex lands. So if I imagine this point from the parent function and it moves 2 spaces to the right, and this point moving 2 spaces to the right, notice that's where those 2 points line up with this new translation. So I find that's one of the trickier ones for students because they have to realize it's going to go in the opposite direction from the way it looks in the equation. Below we have something called vertical stretch. You can't really see vertical stretch if you look at that vertex point, the point 0, 0. You have to look at some other point on the graph to see it. So let's look at the point 1, 1 and compare it to the point 1, 2. Now we looked at this in class looking on Desmos a little bit. And we looked at how when we changed that value in front, it stretched it up. Like somebody grabbed the ends of the absolute value and pulled them up. It made it more narrow. But notice what happened. It's like we took this y value and said 1 times 2 is 2. And that's the new y value. So this is doubling all of the outputs. If I wanted to look at another point, I could maybe look at the point 2, 2. Notice if I took this 2 and doubled that y value, I'd be right here at 2, 4. So this is what's called a vertical stretch. Another important transformation is a reflection, right? Kind of like your reflection in the mirror, except we talk about reflecting across an axis. And in Algebra 1, we're really strictly going to talk about reflecting across the x-axis. Notice the shape of this graph is really the same as the parent function. It's just upside down. That's what we mean about reflecting across the x-axis. And finally, we have what's called a vertical compression. It's sort of the opposite of a vertical stretch. So instead of taking that point and stretching it up, we're thinking of squishing it down. I often think of it, it looks like something sat on my absolute value graph. And basically what that's going to do is it's going to take that arm of the absolute value and sort of open it up to the side. So basically, when I see 1/2, it's going to multiply my x values by 2. This is another thing that kind of works backwards and can be a little bit more confusing. But we can also think about it as taking the y value and multiplying it by 1/2. So notice I gave you the point 2, 1. So if I look at the point 2, 2, and I imagine I take half of that y value, right? 2 times 1/2 is 1. That's what gets me that point. So the vertical compression is multiplying the output by a fraction. All right, let's put some of this to work. When we graph with an absolute value function from now on, instead of having to plug in a zillion values, we want to work with what we call the parent function table. And we want to identify the transformations. So first of all, this little part of the table here is going to be the same for every absolute value problem. We know that when we take the absolute value, we're giving the distance from 0. So the absolute value of -2 is 2. The absolute value of 1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1, and the absolute value of 2 is 2. So every absolute value function starts with that table. And then we look at the problem. See here, one of our transformations is a vertical stretch. We know that a vertical stretch multiplies all the y's by 2 to make them twice as tall as they used to be. So I take the 2 from the first line and multiply it by 2 and get 4. I take the 1 and multiply it by 2 to get 2. Now 0 times 2 is still 0. But 1 times 2 is 2, and 2 times 2 is 4. So these are my new y values. The other thing that I see happening is a vertical translation down 3. So instead of my vertex being at 0, 0, it's going to be at 0, -3. So I'm going to start graphing down here. Then I'm going to look at the points in the table. See how my next point should go over 1 and up 2? So I'm going to start at my vertex and go over 1 and up 2. And then my next point should go over 2 and up 4. So back at my vertex, I'm going to count 2 to the right and 4 up. It also works in the other direction. I go to the left 1 and up 2. And then from the vertex, I go to the left 2 and up 4. Whoops, I went 1 too high. Now I can kind of see that pattern continuing. It's like I have a slope of 2 over 1 on the right, and I have a slope of -2 over 1 on the left. I know my absolute value always makes the V, so I'm not just going to plot the dots. I'm actually going to draw those 2 rays. And it would also be a good idea to label some stuff, definitely at least the vertex.